Okay, today our lesson is on projectile motion with parametric equations. So we're going to be talking about something being launched at an angle, and it has a horizontal distance, which is your x, and a vertical distance, which is your y. Only x and y are plotted. So you have the velocity that it's projected out at, cosine times the angle times t, time. That's your parametric variable. That's your parameter, and it's controlling everything. Then the vertical distance is a negative 4.9 t squared plus magnitude sine theta times t plus initial height. You use negative 4.9 if you're in meters because that's half a gravitational pull, and you use negative 16 if it's in feet. Theta is going to be the angle that it's launched at. The magnitude is the initial velocity that the object was launched. This is the initial height, h, and x is the horizontal distance, and y is the height. Okay, so we'll be using calculators for this, and here we go with an example. So here's a problem. Kelly launched a rocket off level ground, that's the initial height of 0, with an initial velocity of 63 feet per second at an angle of 84 degrees with the ground. After 3 seconds, how far had the rocket traveled vertically and horizontally? And when will the rocket hit the ground? What is the highest point the rocket reaches? Okay, so we're going to write our two sets of equations. These formulas will be given. So we're going to do x equals, and then we have our initial velocity of 63 feet. Then we take that times cosine of the angle 84, and then that's times t. You're going to need to put them in parentheses. Do not forget these parentheses or it'll think 84t is the argument of cosine, which is wrong. Okay, it's in feet, so we're going to use the negative 16 t squared plus the magnitude times sine of 84 times t, and if there was an initial height, we would put that in, which there's not. So what's going to happen is the graph is going to look something like this. The rocket is going to be launched at 84 degrees, which is pretty steep, and it's going to come up and then come back down. This is the horizontal distance, and this is the vertical. Time is controlling everything behind the scenes, but we don't plot it. Okay, here's our 84 degrees. So the first question says, after 3 seconds, how far has it traveled vertically and horizontally? Well, all we do is stick 3 in here. So the horizontal distance will be 63 cosine 84 times 3. And we'll just put that into our calculator. And so I'll just go to run matrix. I'll make sure I'm in degrees. And then I'll just go 63 times cosine 84 times 3. Okay, and the parentheses show multiplication. So that's 19.756 feet. Okay, so this is going to be approximately 19.756 feet. Okay, now we're going to do it with vertical. So now we say y equals negative 16 times 3 squared plus 63 sine 84, and then times 3. We don't need an initial height, so we're just going to punch all this in. So we're going to say negative 16 times 3 squared plus 63 times sine 84 times 3. Okay? So 43.965. So that's approximately equal to 43.965 feet at 3 seconds. Okay, that's your horizontal and your vertical. And then the next question says, when will the rocket reach the ground? Well, we know this is here, so if we just graph the vertical part only on our normal graph and not do it in parametrics, we can see the time. So if I put this equation into my graph, I'm going to do my window at standard just to start. and I do negative 16 x squared plus 63 times sine 84 times x, and I don't have an initial height. Now, since I'm just in a normal graph, my x now is time, okay? So this is not, I'm not graphing it parametrically, I'm just graphing it normally, so x is time. Okay, now that's not a good window. I don't need any negatives, and I need a lot more height showing. So I'll make this like -1, and then I need a lot more height, which is my y, so I'll go to 100 just to see what that does, okay? Okay, that's good. So see how these numbers are so small? This is time. So if I g-solve this and find the root, obviously times 0 was at the ground, and then time, and that's 3.916 seconds. So it hit the ground. You put the y into the graph and find the root. And it was 3.917 seconds. Okay. And when will it hit the ground? And then what's the highest point? Well, I already have this, and it's going to be g-solve max. Now, this is going to be time that it hits the highest point right here, not the horizontal distance, but time. And then this is going to be the height. So it's 61.338. So highest is 61.338 feet. Okay. So there is a way to put this in parametrics, and I will post another video on how to do that.